Welcome everybody to the course on Dynamics and Control. My name is Pedro Albertos from the Polytechnical University of Valencia in Spain. And today we are going to deal with the last part of Module 2. It's like an appendix, and in particular we are going to deal a bit more in detail with mathematics, but not very hard, of course. So we have seen that when we have a signal, we want to represent the signal in a way that is easily treated, stored, manipulated, and so on. The same when we have a physical system, we want to abstract this information and represent the system by means of a model, a mathematical model. Well, in general, this is the problem of abstraction. We have a physical system, we have a signal, and then we want to abstract a model. What is the purpose of that? Well, in principle, the model represents the system or the signal, but is much easier to handle, is much easier to store, to explain, to manipulate. So it's a very good way to handle models and signals. Let's go in a bit of detail with a signal. You remember this sinusoidal signal. So there are a number of parameters, y0, the frequency, the phase, and we can do some operations to sum signals, to make a linear combination, to delay the signal, to compute the derivative or the integral of the signal. And for that purpose, we have seen that the Laplace Transform is a very useful tool to handle these signals. The definition of the Laplace Transform, and you can see on the slide, is apparently very complicated. It's an integral with limits between 0 and infinity and multiplied by e power of minus st. But the nice properties of this Laplace Transform is that first is the unicity. If you have one signal y of t, the Laplace transform is unique, and vice versa. If you have a Laplace transform, the original function on time is also unique. It's a linear operator. What that means that if you apply the Laplace transform to the linear combination of signals, y1 and y2, then the Laplace transform is also the same linear combination of the transforms of these signals. If you consider a delay, y of t, delay τ seconds, then the Laplace transform is the same of that of the signal, but multiplied by the power of minus ts. And there are two very nice properties that we will use also to model processes. The derivative. If the Laplace transform of one signal is y of s, the Laplace transform of the derivative is the same multiplied by s minus the initial conditions. And the integral is the same, but divided by s. So in an operational mode of interpreting this, we can say that derivative is equivalent to multiply by s, integral is equivalent to divide by s. This is not very formal, but is very operational. So we can consider what are the typical Laplace transforms of some signals. For instance, the unitary impulse, the Laplace transform is just the unity. If you have a unitary step, the Laplace transform is 1 over s. And the unitary ramp, obviously, is the integral of the unitary step, so is 1 over s divided by s, so 1 over s squared. And we have also some other very simple and common signals and their Laplace transforms. So you can see here a step which is applied at 1 second. Then the Laplace transform is 1 over s because it's a step. The amplitude is 1 and is delayed 1 second, so it's multiplied by a minus power of minus s. And if you consider the integral, the unitary ramp, then the Laplace transform, as I mentioned before, is 1 over s squared. What about the inverse? If we have a signal y of t and its Laplace transform is 1 over s minus a, then in the general case, when you have a Laplace transform of a signal like this one, you can decompose in partial fractions, just separating by each one of the denominators, and then apply the Laplace transform, which is a linear operator, to the sum of these partial fractions. And then the output is, of course, the result is the sum of two exponentials with the coefficients 2 and minus 2, and with the exponentials minus 1 and minus 2. We can do this similar thing with the discrete time signals. You remember, if we have this sequence of values, then the Z transform using the delay operator was derived like this one. So the Z transform has also similar properties. It's unicity as before, it's linearity as before, and also the delay is just multiplied by Z minus D, if this is the delay. So let's consider this example. We have the signal which is, as you can see in the graphic, is delay 1 unit of time and is constant, value 3. So the Z transform is 3, 3, 3, 3, delay minus 1, minus 2, minus 3. So this is the signal. And then you can sum. And the result of this sum is 3 Z minus 1 over 1 minus Z minus 1. So based on this conclusion, if, for instance, we have a signal like this one, that means that is the sum of the previous one minus 2, the previous one multiplied by Z minus 3. That means delay 3 units of time. So we can derive that this is the signal corresponding to this Z transform. What is the correspondence between continuous time and discrete time signals? In an approximate way, we can say that the derivative is approximately the difference between two sequent values, yk plus 1 minus yk, divided by the sampling period, or the interval t. So if we apply the Laplace transform to the continuous time signal, and we apply the Laplace transform to the discrete time signal, then we guess that S is equivalent to Z minus 1 over t. Well, but in general, we have seen that the delay is interpreted in continuous time like A minus Ts. So in reality, Z is equivalent to E power of Ts. So this is the correspondence between continuous time signals and discrete time signals coming from the continuous time. Let's now move to the processes. And we are dealing with linear, dynamic, time invariant, and concentrated processes. And in this case, you remember the example of the electric circuit with a resistor and a capacitor. We apply the Laplace transform, and then we get the transfer function very quickly. In general, when we describe a system, we will get a set of differential equations, like this one. And if you, based on the properties of the Laplace transform, that means that it's unique, it's linear, and the Laplace transform of the derivative is the Laplace transform of the functions time s, then we get this set of algebraic equations. And then with these algebraic equations, there is no derivative here, we can manipulate these equations very quickly and very easily. Let's see some of the typical situations. Well, this is the same in the discrete time. We have this description, and then the transfer function is, as we saw before, this function, complex function, g of z equal 1 minus over z minus 0.95. So let's see some of the typical situations. First, if we have, say, a series composition of two subsystems, then we can clearly derive that G2 is equal y over x, and G1 is x over u. So putting all together, the whole system composed by these two in series is a unique one with a transfer function equal the product of these two. If we have a parallel composition, then we can derive from this diagram that y is equal the sum of y1 plus y2, and g1 is y1 over u, and g2 is y2 over u, and then all together we derive that the system is equivalent to a single one with a transfer function which is the sum of the transfer functions. We can consider some more complex diagrams like this one, which is a loop arrangement, and in this case it's very easy also to derive this kind of equations. Y is equal GE, M is equal HY, and E is the difference between U and M. And putting all together, we derive the global transfer function of this system, which is not a product, it's not a sum, but it's a more complex composition, a more complex operation, and being more complex means also richer. The loop arrangement is much richer than the series or the parallel arrangement. So another option is to use these models by means of simulation tools. In particular, we are very familiar with MATLAB. MATLAB is a trademark, and you can write very easily. For instance, you have this transfer function. You can write in this way that the transfer function can be expressed, as you can see here, very similarly to the model. And then you can obtain this, which is exactly the same as one. And then you can exploit this model. For instance, applying a step. And then you get the step of this model. And if you remember one of our previous sessions, you will see that this is quite similar to the heating of the kiln, or is quite similar to the filling of the water level in a sink, or it's very similar to the speed or the acceleration of a DC motor. So, by means of this equation, we can simulate the behavior of physical systems. And we will see much more about that in one of our last modules about tools for studying dynamics and control. So, what have been seen today? We have introduced a bit more about mathematics around modeling, not much really, but we have seen that we can parameterize the signal information using the Laplace and the set transforms, and what are the typical transform signals. And in any case, we saw that they are expressed by a ratio of polynomials. And we have also seen the models of systems of operators and in which way we can deal with different structures. And all together will allow us to handle very complicated systems and very sophisticated signals. So what is next? The next, with that we have completed the module 2, and the next will be to analyze the properties of a controlled systems, the dynamic and static behavior, the sensitivity and robustness. And that's all for today.